And every time I press it, it's like right there. Okay, so here's the plan for today, as you can see up on the board. We're going to do a little lesson on slope and equations of lines. Then I want to hit a couple of problems that you had from page 16. And then we'll take any last-minute questions on the function packet. And I'll release who was nominated to be the Facebook person. So, okay. Okay, so let's do a little broad general concept of slope and points and lines and see how that all matches up. Okay, so you would have learned this throughout your years. I'm going to try to just condense it into kind of one little package. Okay, so the first thing we have is this thing called, what is this thing called anyway? When you have an x and a y. It's called a coordinate plane. Technically, it's called a Cartesian coordinate plane. Cartesian coordinate plane. I wonder where that name came from. Cartesian. Such a fancy word. What's that? This is one of those guys. People who are close, read the last names of any of all these guys. Read the names of all of the guys that are up here. Read the names of... What's that guy's name? Okay, his name is actually Rene Descartes. And so he's the guy who came up with this concept, which is really pretty amazing. He lived in the 1600s. And let me tell you a quick story about him. So when he was a little boy, he was really smart, but he was sick a lot. Okay, and when you're in the 1600s and you're sick, you don't go to the doctor and get medicine or anything like that. They say just lay in bed. Okay, so he spent a lot of time just laying in bed staring at the ceiling. Okay, and of course back then people didn't have windows and screens like we have nowadays. So the doors were open, the windows were open, and so there were always flies flying in and all around. Okay, true story. So he's laying in bed just watching the ceiling, and his flies are going all around. And the fly would land on the ceiling, and it would get up and then fly around, plop at another place on the ceiling. And all of a sudden he thought to himself, you know what I could do? I could tell somebody else exactly where the fly is by giving them two numbers. Two numbers. And so he made an arbitrary point in the corner, and he said, I'm going to say the distance that I go this way is one of the numbers, and then the distance I go this way is the other number. And if I just give the person those two numbers, it'll lock right in to where the fly is. What's crazy about that is he was the first guy to do it. Out of all the thousands of years that people have been around, no one had ever thought about mapping a space with numbers. It's crazy. Okay? So, technically, his world, he only lived in the first quadrant. technically. Okay? He only imagined this right here. And the fly would land here, and you give it the two numbers, and bam, there's your point. That's where the fly is. It was only the people that came after him that says, hey, you know what's weird? We could just make this a big number line that goes negative, positives and negatives, and we can make this one go positive and negatives. And then now we have these four quadrants that that we can mark any point with, and then we can actually do some cool stuff with this. Then later on, people turn this into three-dimensional graphs. So now we have three-dimensional space where we have x, a y, and a z, and the whole thing just exploded into a lot of really cool stuff. So, so his name was Rene Descartes, and he was French. How many people are taking French here? Have taken French? Okay, cool. All right, so moving on. So let's take two of the points, okay? If I say here is a point, and I'm going to give it a random coordinate, I'll say x subscript 1, y subscript 1. But from now on, I'll just say sub rather than subscript, okay? Because that's what it is. It's a subscript. And then I'm going to plot out a second point here. We'll call it B. And we have an x1 and a y1. And we're good to go. Okay. By the way, Rene Descartes became really famous for this. And he became so famous. And back then, instead of having huge parties, they would have parades. And so, you know, and have you ever gone to the Christmas parade, the holiday parade here? Okay. Who's the most important person at the parade?
The marching band.
Yes. Aside from the marching band, who's the most important person in that parade? Santa Claus. And where does Santa Claus go? In the parade, where is Santa Claus?
The sleigh.
In the sleigh, but what position in the... It's always the last one, right? Okay, because you're waiting for that. Well, they used to do it differently back then. The most important person actually used to lead the parade. Okay? Back then. And so... So what they did was, Descartes, they're going to celebrate his coordinate plane discovery. They're having a parade, and he's starting off, and he's got, like, you know, donkeys and, you know, stuff people back there. And he's in the front, and he says, okay, let's go. And he starts walking and marching, and he's all excited. And then he looks behind him, and everybody's just sitting there. They're not following him. So he's like, okay, we're going to do this again, round 2. Ready? Yeah. Ready, go. And he's marching, and he's marching, and he's all excited. And again, no one's coming. And so finally, somebody yells out from the crowd, hey, dummy, don't you know you can't put the cart before the horse?
All that build up.
Sorry. Okay. All right. So, moving on. So, now we can plot these points. And so what happened was, someone came along and said, you know what we can do? What if we connect the dots? And what we can actually say is, now we have this rule that says, any 2 points then now define a line. Okay? So we have 2 points determine a line, and we can analyze this a little bit. Okay? What's one of the things that we can analyze when it comes to this line? Genzine. Slope. Okay? Slope. I forgot what slope was. Slope is defined equals rise over run Do we know it as anything else? Change in y over change in x. Anybody know a symbol we use for that? Delta. Delta y means change in. Oops. What'd you say? Triangle. It means a triangle. And anything else that slope's identified as? Any symbol? M. Okay. That makes sense. M for slope. Okay. M, seriously? Some guy who came up with slope, right, had to be named M. Mountain. Maybe because an S looks too much like a 5. I have that problem at times. Wait a second. Wait a second. What nationality was he? He was French. M. Slope in French. Slope in French? Well, I don't know about you, but if I'm going from this point to this point, you know what I'm going to do? I'm going to climb. So, monter is the word to climb, is the verb to climb in French. Is that what you got? No. Yeah. But that's the reason that I believe it is that.
They ran out of letters, so they're like,
Okay. So M represents slope, and it represents kind of the slantiness of the line, right? We use technical words here. So we've often defined it as if I want to go from point A to point B, I can do a rise and I can do a run. And I have to use perpendicular vertical and horizontal lines to get there. Okay? So the question is, everybody see this mistake? Okay. Nobody said anything. Oh. Okay. Then just shout it out. Okay? That's how this class works. So the question is, how long is this segment right here? If you take the y2 coordinate and you minus the y1 coordinate, you're going to get a distance. Okay? That distance, that length, is the amount of the rise. And then this distance right here, that length of that segment, is the x2 coordinate minus the x1 coordinate. Okay? So that's why slope is also then defined as y sub 2 minus y sub 1 over x sub 2 minus x sub 1, rise over run, for any given coordinate pair. Okay? That's the connection and how we see it there. So then the question is, this is like a good visual. Slope is a concept that we have here. By the way, what are the units on slope? If I get a number, this is maybe a slope of 1/2. What are the units on slope? Is it feet? Is it inches? Can it be any of those? Just units? But wait a second. If this is feet, and this is feet, what is the units on slope if it's feet and feet? What are the units on slope if I have feet and feet? It's not feet squared. Huh? If you divide feet by feet, it's nothing. Okay, so let's give a practical example. Here's a point. Here's another point. Pay no attention to it. Okay? What is this? And let's pretend this is measured in feet and this is measured in feet. What is the slope of this line? And including the units. Three minus 1, right? Over 5 minus 2. It's 2 over 3 feet. Feet. Answer? There are no units on slope. Because feet divided by feet is 1. Cancels it out. Cancels out. And the reason why it cancels out is because feet divided by feet is 1. Okay? So therefore, slope has no unit. Now, a huge difference between what you've done in the past and what we're going to do in calculus all year long is that we're going to study slope like crazy, but we're not going to call it slope. Okay? This is a good word I want you to take down, good phrase. Rate of change. Okay? Rate of change is exactly the same as slope. Exactly the same concept. It's rise over run. Okay? However, with rate of change, the units for the two axes are not the same. Okay? The two units are not the same. Okay? So, anybody here in chemistry have taken chemistry? Okay. Done all sorts of things, like you've got some sort of, let's pretend you're going to boil water. Okay? Boil water. Water starts off at this temperature here, and the temperature of the water goes up. Okay? What happens here is we need units. So let's pretend this is degrees Fahrenheit, and this is time, and it's in seconds. Okay? If I want to look at the rate of change from the beginning to the end, and I'm looking at the slope, what I'm looking at is the units here. I don't know, I'm just going to make up some numbers here. Let's pretend this is at 1 second, and this is at, I don't know, 90 seconds. Okay? And then this is 60 degrees, and then this is 80 degrees. Whatever. Okay? And so when you take a look at slope here, you'd say, well, m is equal to, well, it's 80 minus 60 over 90 minus 1. And that's going to give me 20 degrees over 89 seconds. Agree? Look at the units. So what I can say is my answer is 20 89ths degrees per second. When you get a rate, okay, when you get a rate, degrees per second, miles per hour, okay, inches per year, it doesn't matter what. When you get a combination of two different units, it's actually a slope but we don't call it slope, we call it rate of change. Big, big, big deal. I'm going to talk about rate of change, rates of change, how things are changing all year long. Okay, so we got to remember that. When the units are different, it's rate of change. When the units are the same, it's slope. Okay, all the time. All right, well, let's move on here. So at this point, somebody said, you know, well, drawing pictures is kind of cool, but what if we could make an algebraic relationship between these things? So then the concept of algebra got joined with the geometry for the very first time, by the way. It's crazy. There were certain cultures that were really good at algebra, like the Babylonians were crazy, awesome mathematicians. They could do algebra like crazy. The Greeks were awesome with architecture and geometry like crazy. They were just phenomenal. But nobody until Descartes came along said, you know what? These two worlds actually relate. So he presided over the marriage of algebra and geometry. Okay. So now, let's take a look at these lines. More specifically, what is the equation of a line? And what does it mean? So, give me one equation of a line that you know. It's a general form. Y equals mx plus b. Okay? What is this name? What is the name of this? It's called slope-intercept form. Okay? It's the slope-intercept form for the equation of a line, and there's several different kinds of equations of the lines. Okay? The forms. All right, so we know this. The m is the slope and the b is the y-intercept. Okay? And if we have something like this, I don't just make one up, y equals 3x plus 4. Okay? We know what that line looks like. Okay? We can draw that line. But what do the x and the y, what are these things? What do the x and the y do? I know the slope and the y-intercept are those numbers, but what are the x and the y? What is the purpose behind those? Exactly. Any point on the line. What's really cool is if you draw this thing, so 1, 2, 3, 4, and I put my y-intercept, and then I do a slope of 3. Okay, bam, bam, bam. There's an infinite number of points on this line, right? Well, it turns out if you plug the x-coordinate into here, you're going to get the y-coordinate, and it happens to match up right on that line. That's the connection. Okay? And what's cool is we can go beyond lines, and we can draw things like, oh, x squared plus y squared equals, 16. Okay? And with this, it's exactly the same thing. The x and the y represent every single point that satisfies the equation. And if you put them all together, it turns into a circle. Okay? So that's the deal there. All right, let's do another one. Give me another equation form for the equation of a line. Yeah. Yeah. I always forget that one. You ever forget that one? Y sub 2 minus y sub 1 is equal to m times x sub 2 minus x sub 1. Right, Dad? What's the name of this one? This is called point slope. Why is it called point slope? Gives you a point and a slope. Actually, it's y minus y sub 1 and x minus x sub 1. I told you I don't remember that one very well. But you know what? I don't really need to, because what did we define this as? This was y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's the slope, right? So I always just write slope because that one I know, and then I just cross multiply. And I say x sub 2 minus x sub 1 times m is equal to y sub 2 minus y sub 1. And would you look at that? Actually, you just take the slope formula and you cross multiply, and you get point slope form. You see it? Okay. And we just happen to be using a random point here, but there it is. Okay. So point slope form for the equation of the line looks like that. Okay. Another one. AX plus BY equals C. This would be called standard form. Okay. And then there's another one. You see AX plus BY plus C is equal to 0. These two get confusing. Okay. And then we have vertical lines. What's the equation for a vertical line? X equals something. What should we make x equal? How about x equals a, where a is an element of the set of all real numbers? Okay, where a is a real number. Now that's weird. Why is it just x equals? How does that work? So if you make a t-table and I say, guess what? No matter what, x is 3. Doesn't matter what it is. Then I guess y gets to be whatever it wants to be. Okay? And so I can put all these numbers, 3, 1, 3, 2, 3, 3. And if you happen to plot these, 1, 2, 3, then where you're getting this line, this point, this point, this point, and then so it actually just forms right there because x is always the same. Okay? So vertical lines look like that. Horizontal lines, y equals, we'll call it b this time. B is an element of the real numbers. Okay, slope of a horizontal line. Slope of a horizontal line? 0. Think of it, how much rise do we have on a horizontal line? No rise, 0. Okay, so 0 rise. On a vertical line, how much run do we have? None. Okay, so you take a number and divide it by 0, whole world blows up, and then we got problems. Okay, just don't do it. Okay, and then of course we have intercept form, which is 6, which is x over a plus y over b is equal to 1. 7. Don't worry, I was never good at numbers. Okay, this one is called intercept form. And you all know what I'm talking about because this was in your homework, right? Mm-hmm. Well, let's take a look at it. The way it's defined is that A is the x-intercept and B is the y-intercept. A is the x-intercept and B is the y-intercept. So let's take a look at this. So I can go out here some way on the x, and the point has to go, the point in the line has to go through that point. And then B is over here. Okay? It's B high, and that's the y-intercept. And so the line that passes through that has the equation x over a plus y over b is equal to 1. Good? I'm going to make up a lot of stuff for you guys. Everybody agree with that? This is going to be fun. We good with that? Lindsay.
Why does it equal 1?
Oh, okay, well, let's take a look at this. So if I start off with x over a plus y over b, let's try to prove that it's equal to some line that maybe we can recognize. So what I'm going to do is I'm going to try to put this equation right here into the form y equals mx plus b. And if we can, then we can see if this works over here. Okay? It's kind of like the identity thing which you did back last year in trig, how to prove that one thing is equal to another thing. We do that a lot here. What I'm going to try to do is I'm going to take this, algebraically manipulate it to get to this. Because equations, they were born to be manipulated. Okay? All right, so I need some help though. How can I solve this? How can I put this into this form? What should I do? Solve it for y. Subtract the x over a. Okay, let's do that. So I got y over b is equal to 1 minus x over a. Does it look like this yet? Almost. Okay, what next? So we have this thing, it's pretty cool. It's an algebraic equality. It says that if you can multiply equal things by equal things, and the answers are equal. Multiplication property of equality. So if these two things are equal and I multiply them by equal things, the answers are still equal. All right, so here I get b over b, which is 1, so I get y is equal to, I'm going to do a little distributive property, b minus b over ax. Would you agree with that? Okay. Does this look like this exactly? No, but with one step I think we can do it. Y is equal to negative b over ax plus b. So the question is this line that line? And if so, explain. Y-intercept? B. Slope of this line. What's the slope of this line? I got to go down B and over A. Negative B over A. So what we just proved here is that x over A plus y over B is equal to 1. That is the equation of this line right here, because we proved that it's equal to this one right here, which we understand, the y equals mx plus b. Okay? This is called the intercept form, and it actually matches what you guys learned last year when you studied conic sections. Does this look familiar? X squared over a plus y squared over b is equal to 1. I think these were squared. That look familiar? What is that the equation of? It's the equation of an ellipse. Okay? Where a is So if we graph this here, and I draw this like little ellipse right here, this right here is A. That's the distance here. This distance right here is B. Okay? It's the equation of an ellipse. And by the way, if A and B are the same number, it's a circle, and the radius is equal to both the A and the B values. Okay? And if you switch this to a minus, it's the hyperbola, yes. It's the hyperbola. Okay? All right. Equations of the lines and all of the different forms. That's a recap of what we did, what was in that section. Today's Tuesday. Tomorrow is Wednesday. Tomorrow I want to see page 27. And we'll be moving on. And start to expect maybe a little quiz on your functions. But I'll wait until we take any last questions tomorrow. So we'll just pick up where we left off tomorrow. Oh, Megan was nominated.
I already made it. She already made it.
Go figure.